Hi everyone. Now that we've got a couple rules under our belts, we know how to use the power rule, the product rule, and the quotient rule, and we know about our trig derivatives. We're going to be talking about a last rule called the chain rule, which will help us differentiate different types of functions that I've kind of purposely stayed away from at this point. So we'll just kind of investigate a problem, and then we'll see what the rule is and look at some examples using that rule. So if we wanted to find the derivative of f of x is equal to the quantity of 2x plus 1 squared, what we would probably likely want to do would be to multiply out and use our power rule. So that would be 2x plus 1 times 2x plus 1. We could also use the product rule here if we wanted to, but it's probably just as easy to just FOIL that out. So that would give us 4x squared plus 4x plus 1. And then we could take the derivative from there just using our power rule. So that will give us ex plus 4. Okay, well, would we be able to use the same strategy to find the derivative of something like this? So what if I had the square root with a quantity underneath it? Well, I know that I can rewrite that as f of x equal to the quantity of x squared plus 1 raised to the 1/2 power. But algebraically, we don't have kind of a thing that we can do with that 1/2 power like we do with the power of 2. So for right now, our answer is no. We can't use that same strategy. It's not going to work for us here. So in order to get the derivative of something like this, we use something called the chain rule. And the chain rule is basically existing because it will allow us to take derivatives of composite functions. Because if we think about this, this is really an inside function of x squared plus 1 underneath an outside function of a square root. So there's really an inner function and there's like an outer function. So the chain rule allows us to take the derivative of a composite function. So if we have some composite function defined by f of x and we call that f of g of x, then we would say that the derivative, or big F prime of x, is going to be equal to the derivative of the outer part of our function with the inner part staying exactly the same times the derivative of the inner function. So this first part is the derivative of the outer function while the inner function stays exactly the same. And then this piece over here is the derivative of the inner stuff. So let's take a look at an example using this chain rule. So for this function in example 1, this is definitely an inside function of x to the 4th plus 9 inside an outer function of like a something raised to the 7th power. So this is definitely a composite function. So when I take the derivative or find my f prime of x, I'm going to first just apply the power rule on the outside piece here. So the outside piece is that exponent of 7. So I'm going to bring down the 7. I'm going to leave the inside stuff exactly the same. And I'm going to, again, keep on applying my power rule that says that once I drop down that exponent, I do have to decrease it by 1. And then the chain rule says I also need to take the derivative of the inner stuff. So I've taken care of the outside stuff. Now I'm going to concentrate on the derivative of the inside stuff. So just the x to the 4th plus 9, I want to get the derivative of, which would be 4x to the 3rd power. So here's my derivative of my outer. And here's the derivative of the inner. And I'm just going to clean that up a little bit. So I'm noticing that I've got a couple like terms that I can multiply. So like the 7 times the 4 can clean up to be 28. Generally, I pull any like single variables with exponents out to the front. And I'll leave that x to the 4th plus 9 raised to the 6th as it is. So f prime of x is 28x cubed times the quantity of x to the 4th plus 9 raised to the 6th power. So let's look at a different example. So our next function that we want to take the derivative of is cosine of x cubed. So usually, or the derivatives that we were taking last week only had just x's in here. And there was a reason for that, because if there was anything other than x, we would have had to apply the chain rule, which we didn't know how to do yet. So my outer function is just this cosine on the outside. So I know the derivative of cosine is negative sine. Again, I'm going to open up the parentheses and I'm going to leave that stuff exactly the same on the inside. And then I'm going to multiply it by the derivative of the inside stuff. So the derivative of just that x cubed is what I want to multiply by. So that would be 3x squared. So again, here's the derivative of the outer part with the inside stuff staying exactly the same. And here's the derivative of the inner stuff. And again, I'm just going to clean this up a little bit just to write it a little bit nicer. So f prime of x is going to be equal to negative 3x squared times sine of x cubed. All right. So example 3 is asking us to find dw dt. So remember that this is taking the derivative of w with respect to t. And we're told that w is equal to tan x and x is equal to 4t cubed plus t. So what we actually have to do is we actually have to form a composite function first. I need to get a function of w with respect to t. So what I'm looking for is a w of t. Well, my w function is tan of x, but I know what x is equal to. X is equal to 4t cubed plus t. So my composite function, w of t, would be tan of 4t cubed plus t. And I want to find the derivative of this. So dw dt is going to be equal to, and again, I'm just looking at the derivative of the outside stuff, so the only outer function here is tangent. I know its derivative is secant squared. The stuff on the inside is going to stay exactly the same. And then I'm going to multiply by the derivative of this inside piece. So the derivative of this inside piece would be 12t squared plus 1. And since that is a binomial, I'm just going to keep it on the inside of a set of parentheses just to make sure that I'm separating it from the other stuff. And just in general, I like to rewrite these with the trig stuff at the end. So I would just for the sake of how I do it, pull that 12t squared plus 1 out front. And then that would be multiplied by secant squared of 4t cubed plus t. All right, so let's look at example 4. So we want to find the derivative of f of x is equal to tan squared of x. What I like to do with trig functions with exponents on them, I like to rewrite them a little bit differently just so that I'm recognizing exactly what the outside function is. So just know that tan squared of x is the same thing as the quantity of tan x squared. And that allows me to recognize that that power of 2 is my outside function and the tan of x is my inside function. So when I take the derivative here, the outside function, I'm just applying my power rule. So I'll bring down the power of 2, multiply that by tan of x, decrease the exponent by 1. So that's really just an exponent of 1 here. And then multiply by the derivative of the inside stuff. So multiply by the derivative of tangent, which is secant squared. So outside derivative, inside derivative. You do not need to keep the parentheses there with the tan x. So you can just write that as f prime of x is equal to 2, tangent of x, secant squared of x. All right, let's take a look at one more example and then we'll look at some sort of applications here. So our example 5, I'm noticing that we definitely have a quotient here, but I'm going to actually rewrite this so that we actually don't need the quotient rule. Anytime you have like a 1 in your numerator and you just have stuff in the denominator, it is definitely okay to say that that is the same thing as f of x is equal to the quantity of x to the fifth minus x plus 1 raised to the negative ninth. So basically what that negative is doing is that's actually moving that up to the numerator with that negative exponent. So here, the reason that I like doing this is because that simplifies my work so much more than actually having to use the quotient rule here. So my outside function is this negative 9 exponent. So I'm going to want to use my power rule on that. My inside function is this x to the fifth minus x plus 1. So I'm going to go ahead and start using my chain rule. So I'm going to bring down that exponent to be a negative 9 times the quantity of x to the fifth minus x plus 1. Decrease that exponent by 1. So it'll give me an exponent of negative 10. And then I want to multiply by the derivative of the inside stuff. So I want to get the derivative of this stuff inside. So that'll be 5x to the fourth minus 1. And again, since this is a quantity, a binomial, I am just keeping it in a set of parentheses. I'm going to clean this up a little bit. So I'm going to bring the negative 9, and then I'll bring this 5x to the fourth plus 1 kind of out front. And then I'll leave this x to the fifth minus x plus 1 raised to the negative 10th at the end. We can go ahead and distribute this negative 9 out to just the first parentheses. We don't want to do it to the second because the second has an exponent on it. This first one does not, so it's okay to distribute. So that'll be negative 45 x to the fourth minus 9 times the quantity of x to the fifth minus x plus 1 raised to the negative 10th power. And if this was just kind of like an open-ended or a free response question, I would be okay with you keeping it like this. Sometimes you might actually need to manipulate this a little bit. So if you did need to manipulate this a little bit, you can bring down that quantity that does have that negative exponent on it to the denominator. So you could rewrite this as negative 45 x to the fourth minus 9 up top, and then the quantity of x to the fifth minus x plus 1 to the positive 10th would be the same thing. So just know that either of those are equivalent expressions. All right, so let's look at some tables, and then we'll look at an equation of a tangent line that'll have you guys try some on your own. So we're given a table of values. We're given a whole bunch of values here. We know for part A, we're looking for f prime of 3. We're given an expression for f of x. We see it's a composite function, so we're definitely going to need to apply our chain rule here. So the first thing I'm going to do is I'm going to write a rule for f prime of x. So I'm going to take the derivative of this. So the derivative of the outside function would be my f. Keep the inside of g of x the same. And then multiply by the inside piece's derivative. So multiply by g prime of x. So again, if you notice, that's just the chain rule. So if we're evaluating f prime of 3, that will be f prime of g of 3 times g prime of 3. So the first thing I want to evaluate here would be the g of 3, which if I look in my table, g of 3 is 5. So I want to evaluate f prime of 5 next to my step, and then I'm multiplying that by g prime of 3, which would be 7. So f prime of 5, if I look back up here at my table, would be negative 1, multiplied by 7 would be negative 7. All right, let's look at another one. So now we're looking for g prime of 3. We're given a different expression for g of x. So I'm going to go ahead and write a rule for my g prime first. So again, composite function, I should be applying the chain rule. So the derivative of the outside piece would be g prime with the inside stuff exactly the same. Multiply by the derivative of the inside stuff. So multiply that by f prime of x. So then I want to evaluate that at 3. So g prime of f of 3 times f prime of 3. First thing I want to evaluate in here would be f of 3. If I look at my table, f of 3 would be 5. And then I want to fill in g prime of 5. G prime of 5 would be 4. And I want to multiply that by f prime of 3, which would be negative 2. So it will give me a negative 8. All right, and the last piece that I want to go through with you is finding equations of tangent lines, because we can use the chain rule even with questions like this when we're finding tangent lines. So we want to find the equation for the tangent line to the graph of y is equal to x cosine of 3x at the point where x is equal to pi. So I know I'm looking for a tangent line, so I know I'm looking for a derivative here. And I'm noticing that I do have a product. My product is x times cosine of 3x. So I'm going to call my f my x, call my f prime 1. I will call my g cosine of 3x, and I will call my g prime. And here I'm going to have to apply the chain rule. So my derivative of my outside stuff would be negative sign. Keep the stuff on the inside exactly the same. Multiply by the derivative of the inside stuff, which would just be 3. So my g prime would actually be negative 3 sine of 3x. So once I apply my product rule here, that will give me f prime times g. I want to add to that my f times my g prime, so x times negative 3 sine of 3x. And I'm just going to write this a little bit nicer. So y prime would be equal to cosine of 3x minus 3x sine of 3x. Okay, so there's my derivative. I'm looking for the equation of the tangent line at the point where x is equal to pi. So I'm going to take my derivative, what I just got here, and I'm going to evaluate it at pi to get my slope. So cosine of 3 pi minus 3 pi times sine of 3 pi. On my unit circle, 3 pi, the cosine there would be negative 1 minus 3 pi times the sine of 3 pi. Sine of 3 pi would be 0. So it looks like my f prime of pi, or my slope at pi, would be negative 1. So then I want to know what the y coordinate of this point is, because in order to write my equation, I do need to get the y. So I'm going to go back to my original function and evaluate that at pi. So that'll be pi times cosine of 3 pi. And we already know cosine of 3 pi is negative 1. So it looks like our y value of our point would be negative pi. So we've got a slope of negative 1, and we've got a point at pi, comma, negative pi. So that would mean that our equation in point slope form would be y plus pi is equal to negative 1 times x minus pi. Okay, so what I'm going to have you guys do is I'm actually going to have you stop the video, and I would like you to try these problems. So 1A, B, and C, and then number 2 down at the bottom. And I would like you to, once you're done, start back up the video, and I will work through these solutions for you. All right, so we are looking for dy dx. So here, my dy dx for example A, my outside function is the power of 10. So that'll be 10 times x squared plus 5 to the 9th when I decrease the exponent by 1, multiply by the derivative of the inside stuff, so 2x. And then I'll just clean that up a little bit. So dy dx would be equal to 20x times x squared plus 5 raised to the 9th power. Second example, I'm actually going to rewrite as the quantity of 1 plus 6x raised to the 1/2 power, just so that I am, again, having a clear idea of what the outside versus the inside function is here. So my outside function would be the 1/2 power, inside function would be the 1 plus 6x. So dy dx here, I'm going to bring down that exponent, so 1/2 times 1 plus 6x, decrease the exponent by 1, that'll give me a negative 1/2. Times the derivative of the inside stuff. So derivative of 1 plus 6x would just be 6. So dy dx would be equal to 1/2 times 6 will give me 3 times 1 plus 6x raised to the negative 1/2. I'm just going to clean that up a little bit. So I will say that's equivalent to dy dx is equal to 3 over 1 plus 6x raised to the positive 1/2. And if I wanted to go one step further, I could turn that back into a root. So 3 over the square root of 1 plus 6x. All right, and our last example up here at the top, derivative of sine of 3x plus 2. Outside function is sine, so its derivative is cosine. Leave the inside stuff exactly the same. Multiply by the derivative of the inside piece, which would just be 3. So our dy dx would be equal to 3 cosine of 3x plus 2. Okay, and our last piece here, similar to what we did in the chart, except I just gave you values up here. So we're looking for h prime of 2. We're given a composite function for what h is equal to. So first thing I'm going to do is write out a rule. So h prime would be equal to g prime of f of x times f prime of x. So if I want to evaluate h prime of 2, g prime times f of 2, or sorry, g prime of f of 2 times f prime of 2. So first thing I want to evaluate here would be this f of 2, and our values above that is telling us that's a 3. So I want to evaluate g prime of 3 times f prime of 2 would be 4. So g prime of 3 is negative 5 multiplied by 4, give me a negative 20. Okay, and then in example B, we're looking to evaluate k prime of 3, where k of x is equal to this composite function. So here you'll notice that we have a 1/3 on the inside here. That's going to change our derivative just a little bit. So k prime of x, I'm going to write a rule first. Derivative of the outside, so f prime. Keep the 1/3 g of x on the inside exactly the same. And then the derivative of 1/3 g of x would actually be 1/3 g prime of x. So think about that 1/3 as just being a constant. Remember that we always just kind of like pull those down with the function when we take the derivative. So k prime of 3 is asking me to do f prime of 1/3 g of 3 times 1/3 g prime of 3. So first thing I'm going to evaluate in here is what g of 3 is. And I'm going to end up multiplying that by 1/3. So g of 3 is 6 times 1/3 g prime of 3 is negative 5. If I clean that up a little bit on the inside here, 1/3 times 6 is 2. And then I'm multiplying that by negative 5/3. F prime of 2 is 4. Multiplying that by negative 5/3 is going to give me negative 20/3. All right, so your homework is listed on the bottom here. It is in the textbook. The even answers I will be posting at some point this weekend, but if you do have questions on anything as you're working through these problems, make sure that you let me know. There we go. It's in focus. All right, hope you have a nice weekend.